Hello everyone, my name is Samuel Matloop and this is a presentation about element distinctness lower bound. It is for course COT 5405, Design and Analysis of Algorithms for Fall 2021. The first thing that we're going to talk about in this presentation is the problem itself, kind of a description to the problem. What are we trying to solve, or what are we trying to improve upon? And once we get this out of the way, then we're going to talk about the proof overview, where we state the claims that we're going to be using during this presentation and proof. And once we finish that, we'll jump into the proof detail, where we start talking about the decision tree model, the geometry representation, and the connected and convex regions. And then we'll talk about each claim in more details. And at the end, we're going to be summarizing everything that we talked about in this presentation. So what is the problem? The problem is, given an array A, we need to check if each element of the array is unique and distinct. The trivial solution to the problem is going to be sorting the array and then checking and comparing each element to the adjacent element. This solution is going to take a time complexity of n log n. But the question is always going to be, can we do any better than this? Can we do any better than n log n? And the answer to the question is no. This presentation is going to show and conclude and prove the lower bound of such problems. And we'll conclude that the best we could do is going to be n log n. Our proof is going to make three claims. The first claim is we're going to take a region, R of L, in which a leaf L is reached, and we claim R of L is connected. And we're going to explain in the upcoming slides what connected regions mean. The second claim is if we take X, an array that consists of distinct elements, and if we take Y, a permutation of X, meaning the elements of Y is going to be the same of elements of X but in a completely different order, then X and Y must reach distinct yes leaves or distinct solution. The third claim relies on the second claim, and we claim that the number of yes leaves or the number of possible solutions is going to be greater than or equal to n factorial. And if so, we will conclude that the lower bound of such problems is going to be n log n. Alright, so let's talk about the decision tree model a little bit. To the right, there is a flowchart of a decision tree model that represents a sorting algorithm of three elements, A, B, and C. And at the root, we have A and B compared, and if A is greater than B, then we're going to take the left path, in which we're going to compare A to C, and if A is greater than C, then we're going to take the right path this time, and we're ending up on a leaf that is denoted by C greater than A greater than B. Please notice that there are 6 leaves in this problem. And the more elements we have, the more leaves we will end up with in the model. And in general, if we have n elements in the problem, in the sorting problem, we will have n factorial leaves. Each leaf is a possible solution. One of the leaves is the solution for the sorting problem. And the worst case scenario to find a solution for a sorting problem is going to be traversing the tree model from top to bottom, basically traversing the height of the tree. And the height of tree is log n factorial, or can be simplified to n log n. And that is the time complexity for the sorting algorithms. Now shifting away from the sorting algorithms and moving to the element distinctness problem, it's a quite different, and the reason being is because with the element distinctness, if you think about it, it only has two possible solutions, and therefore it only has two leaves in the decision tree model. So a leaf that says yes, that means the problem or the model found a distinct array, or the leaf that says no, and that indicates that the array is not distinct, or the elements are not distinct in the array. And because of that, we only have two outputs, and if we try to apply the previous formula with two outputs, we will end up with a constant time complexity. And that is far away from the truth. And therefore, we will have to adapt a new strategy to be able to study the element distinctness algorithms. And therefore, we're going to interpret X with n elements as a point on an n-dimensional space. And therefore, if X has two elements, the first element is going to represent the x-axis, and the second element is going to represent a value of the y-axis. And if X has three elements, then it will represent the x, y, z coordinates accordingly. We will restrict the values of X to simplify the process such that xi will be between 0 and 1. This slide shows the representation of X with two elements, and therefore we see a two-dimensional diagram here where x1 and x2 varies from 0 to 1, forming a square shape. Please note that the diagonal of the square in red color represents points represents all the points where x1 equal x2. And therefore, these points are going to land on the no leaf in the decision tree model, while the points to the right of the diagonal or to the left of the diagonal that are colored in green are going to be ending on the yes leaf, as x1 and x2 are unique, distinct, and different. Now we're going to talk about the first claim. That is, if we take a region, R of L, in which leaf L is reached, R of L is connected. A region R is connected if for any points x, y belongs to R, there exists a path from x to y passing entirely through R. There is another type of region called convex region. A region R said to be convex if for any points x, y belongs to R, the straight line path from x to y passes entirely through R. Therefore, convexity is a special case of connectivity, and convex region is connected region too. Alright, going back to the decision tree model, I wanted to mention the fact that the region that we were talking about is actually the path from the root to the different nodes down to the leaf. That's what the region represents in the decision tree model. Every time that we move from one node to another node, the geometrical model that we created for our problem is going to get sliced. For example, the cubic to the left shows the case when x3 is less than x1. Condition applied, and the new part becomes the part that comes out from the red dotted rectangle. The slice, the new part, is also a convex and therefore connected region. And the proof to this claim is quite simple. If we take an instance x that reaches L, and we take another instance y that reaches L as well, that means both x and y are taking the same path, and we take instance z such as zi equal c, a constant, multiplied by xi plus 1 minus c multiplied by yi, where c is between 0 and 1. And we'll notice that if c equal to 0, that means zi equal to yi, while if c equal to 1, then zi will equal to xi. And we're kind of making z as a straight line between or from x to y. So if we let the root ij, and suppose that the branch that we're going to take is going to be the less than branch, so I is less than j, then xi is going to be less than xj. The same thing applies to y, and hence yi is going to be less than yj, because they both kind of follow the same path, since they both reach the leaf L. If we multiply the first inequality by c and multiply the second one, which is yi less than yj, by 1 minus c, and add both inequalities, we can conclude that zi is also going to be less than zj. And that means z is also going to go to the same path as x and y. And we can track that down to the leaf. And that means in every step, in every node, and in every slice, when we apply the condition to move from one node to another node, there is always going to be a straight line from x to y. And that means that the new part, or the new model, from slicing is convex, or represent a convex region, and it's also connected. Alright, so now that we have proven our first claim, let's go ahead and try to prove our second claim, which states that if we take x that consists of distinct elements and take y that is a non-trivial permutation of x, then x and y must reach distinct yes leaves. So what do we have here? We have x that comprises of distinct values, which means x path is going to end with a yes leaf, and therefore the answer of x is going to be equal to yes. And we have a y that is some permutation of x, and that means y is going to take a path that ends with a yes leaf as well. And therefore the answer of y is going to equal to yes. We can prove our claim using proof by contradiction. And we can assume both x and y to reach to the same leaf L. And because R of L is connected, therefore there must be a path z that belongs to the region from x to y exist. So let's take xi less than xj, and let's take yi greater than yj, which most likely happens and possible since y is only a permutation of x and the elements of y is in a completely different order than x. Then yi could be very well be greater than yj. And so let's define a function f of w equal to wi minus wj. And therefore, f of x is going to be less than 0 since xi less than xj, and f of y is going to be greater than 0 because yi is greater than yj. From the intermediate value theorem, and because the function f of w is a continuous function, therefore there must be a point z belongs to the path such that f of z is going to equal to 0. But if f of z equal to 0, that means zi is going to equal to zj, which means the elements are not going to be distinct, and therefore the path that z going to take is going to end to a no leaf, and therefore the answer of z is going to be no, which is a contradiction since x and y are both reaching or going to reach to the same yes leaf, and the region is connected, then z should be also ending with a yes leaf. But what we see here, z is reaching to a different leaf, a no leaf, the contradiction. And therefore, the assumption that we have made is incorrect, and therefore x and y are going to reach to a distinct yes leaf and not going to reach to the same leaf. So what do we know so far? We have proven our second claim, and now we know that if we take x, and x consists of distinct elements, and if we take y and make y a permutation of x, then x and y must reach to a distinct yes leaves. And because we know that there are n factorial of possible permutations, we know, or we can conclude, that there will be at least n factorial number of yes leaves. And therefore, the time complexity for such algorithm is going to be n log n. And we just proven the lower bound for the element distinctness problem. To summarize what we have talked about during this presentation, we started with a talk about the problem and a description to the problem, and then we moved to a proof detail starting from the decision tree model, geometry representation, as well as talking about the connected and convex regions, and down to the claims and their proof. Finally, the reference I used for the topic that was covered by this presentation is a YouTube video by Professor Randay with a title of Lecture 25, Element Distinctness, Lower Bounds. Thank you very much for watching, and feel free to reach out for any questions.